IPv4 is pretty old. It's been around for about 40 years at the time of recording this video. So it's been around for quite some time. And one of the major drawbacks of IPv4 is that we're running out of addresses. It's funny, for the last probably 15 years, we've heard about how next year was the year we're going to run out of addresses on IPv4. But it never seems to come to fruition, probably because of things like CEDAR addressing and natting and things like that. So I think the problem's been a little bit overstated, but for sure, it's IPv6 is a superior technology for a variety of reasons, not just the limitation in address space in IPv4. So an IPv6 is very different from an IPv4 address. You don't have to worry about mixing them up; they look completely different. And the problem with IPv6 is it's not widely implemented in local area networks. So there are some technologies that allow us to use both IPv6 and IPv4 in the same environments. So we'll talk a little about that and how to transition from 4 to 6. So originally named IP Next Generation, IPv6 was created in 1994 by the IETF. So 1994 was a pretty long time ago now, right? So good grief, 1994 was well over 20 years ago, and we're still not really fully implementing IPv6. One of the things that IPv6 gives us is a larger address space. It's also a hierarchical address space, meaning you can have some degree of hierarchy with IPv6 addresses. In IPv4, you really just have the host and the network portion, and that's pretty much it. It does support auto configuration, and that's supported natively within the protocol, as opposed to IPv4, where we have to use things like DHCP. It has built-in quality of service support, built-in support for security. It actually has encryption built into the standard. Has better support for mobility, extensibility. So in IPv4, we use subnetting, but it's really no longer applied to IPv6. So we really don't use subnetting in IPv6. It uses 128 bits instead of 32 bits for an address. So that's significantly more address space than an IPv4 address. So it's much longer. Of course, it's also much more difficult to memorize IPv6 addresses. IPv6 addresses are written as 8 16-bit hexadecimal numbers separated by colons. So it'll look something like this. You'll notice that in some of these, there's you don't see all 16 bits. That means that there's zeros in the front of that. And the zeros, of course, are optional. You don't have to write the zeros. So some things about the IPv6 address is one or more consecutive zero values could be written as a double colon, so 2 colons right after each other. But you can only have one of those per address. Leading zeros are optional, and hexadecimal numbers are a little bit easier to convert to binary, so we use hexadecimal numbers in IPv6 as opposed to using decimal numbers in IPv4. So the interface ID of IPv6 is typically 64 bits and uses the interface's 48-bit MAC address for most of the address, and then it's a 16-bit value that is inserted after the first 24 bits of the MAC address. So you can use part of the MAC address, or the MAC address really, as part of the IPv6 address, because we have such a huge space, and that helps us ensure unique addresses. So the first 2 zeros in a MAC address can be replaced with 02, and then there's also auto configuration. So the auto configure 64-bit host ID is referred to as the extended unique identifier 64 interface ID. And again, this can be automatically generated because we're using part of the MAC address to make that unique identifier. The IPv6 address is entered manually into the interface's property dialog box, so that's another option for setting your interface ID. So a unicast address, just like an IPv4, a unicast address is a specific interface on a device. There's 3 primary types, though. Unlike our IPv4, we have 3 different types. We have a link local address, which is sort of like our local loopback in IPv4. It's used for computer-to-computer communication. You have unique local. I'm sorry, I misspoke there. The link local is for computer-to-computer, not a local loopback. Unique local is the address starting with FC or FD that are used for behind a firewall and are pre-configured on routers. And then global is an address that can be used accessible from the internet, so routed from the internet, from the public internet. So a loopback address, we do have loopbacks on IPv6, just like in IPv4. In IPv4, it's 127.0.0. whatever. In IPv6, it's ::1 for the loopback address by default. So in the in IPv6. So documentation, the global unicast address is reserved for use in books and other documentation addressing IPv6, so you can't use that one or that range of addresses. All right, so and then IPv4 to IPv6 transition, there's several address prefixes that are used for transitioning from IPv4 to IPv6, which we're going to talk about here in just a few minutes. We'll get to transitioning in a little bit. So subnetting with IPv6, as I said before, we have such a large address space in IPv6, it really obviates the need to do subnetting. So most allocations just have a 48 prefix. So it leaves 80 bits for assigning subnets and host IDs. 80 bits allow 16 subnet bits, since the interface ID requires 64, and that allows up to 65,536 subnets, which is pretty significant. So this is the typical structure of an IPv6 address. You have the global routing prefix, which is the first 48 bits, then the subnet ID, which is 16 bits, and then the interface ID, which is the following 64 bits. And that gets us to our total 128 bits for an IPv6 address. A multicast address in IPv6 is the same as multicasting in IPv4. They typically begin with FF, and they have the structure that looks like this. So FF tells you that it's a multicast address. The next character is a 4-bit field, which here is shown as the X. And then the scope is indicated with a Y. It specifies whether and where the multicast packet can be routed. And then the group ID is represented by the Z characters. So you would have a group ID for the multicast address. So you can be pretty sure that if you see a IPv6 address that begins with FF, that is a multicast address. An Anycast address can be assigned to multiple interfaces on different nodes. They're recognized as Anycast addresses by the devices that use them. So they are assigned on routers and are used to allow IPv6 nodes to deliver packets to the nearest router on a subnet. In other words, multiple devices can listen on a certain IPv6 address. So you don't have to have all either multicast or unicast. You have this Anycast concept, which again allows you to set the same address on multiple devices. You really can't do that in IPv4. You can't have the same address on multiple devices. So this is an interesting concept in the IPv6, that you can have multiple devices that have the same IP address. So it's not quite a multicast, but it's also not unicast. They don't really have any special format. You just have to be aware that those addresses are Anycast addresses. So just like in IPv4, you can do auto configuration in IPv6. Thank goodness, because who wants to type in these huge numbers, right? They're pretty long, these IPv4 addresses. You have stateless auto configuration, where this is where the node listens for router advertisement messages from a local router to assign its IPv6 address. And then stateful is where it uses DHCPv6. So there's a newer version of DHCP which supports IPv6 and handing out IPv6 addresses. So either one of these methods could be used to auto-configure an IP address. Stateless auto-configuration is really built into IPv6, whereas DHCPv6 is a different standard. It lies outside the IPv6 standard. So on a Windows host, if you configured IPv6, first it's going to initialize, it's going to do a link local address that it's going to determine. So it's going to make up a local address, the link local address. So link local, if you recall, is for computer-to-computer addressing within your subnet, just between computers, so no routing. So there's no ability to route. So it's going to assign its link local address, which is then going to make sure that there's no duplicates on the network. So you can detect if there's duplicates. That works in IPv4 as well, by the way. Once it's verified that it has a unique link local address, it's going to assign it to the interface, and then it's going to send a router solicitation message. So that's going to use that stateless method to try to determine what its IPv6 address needs to be. But if nothing responds to that router advertisement message, then it'll fall back to DHCPv6 in Windows. This isn't how all IPv6 devices work. This is just how Windows works. So in Windows, it'll try DHCPv6 if it can't connect to if the router solicitation message fails to get a response. If it did get a response from the router solicitation message, then it will use that response to set the IPv6 address. So again, two methods to set our IPv6 address automatically. But remember, first it's going to create its link local address, verify it's unique, and then it's going to use that to try to go out and find an IPv6 address, either using the stateless or stateful method, which again is either router solicitation or DHCPv6. So the problem with the IPv6, it's not widely implemented first. although it's gaining more traction. At the time I'm recording this, I'd say that probably the vast majority of corporate networks are probably still on IPv4. But a lot of folks will say, well, we support IPv6 on our network, and typically that's done through some kind of transitioning protocol or through some kind of tunneling with IPv4. So basically what happens here is we can't just go cold turkey from IPv4 straight to IPv6. We have to have some kind of transition to get there so that both protocols will work at the same time. So starting in Windows 2008 and Vista, we supported Windows supported IPv6 and started supporting this dual IP layer architecture. So some of the technologies we'll talk about for dual IP architecture: IPv6 over IPv4 tunneling, intra-site automatic tunnel addressing protocol, or ISATAP, and 6-4, and Teredo, which is probably one of the better standards. It's got kind of all the bells and whistles of those different methods. So the dual IP layer architecture means that the computer can communicate directly with both IPv4 and v6 devices using native packet types. In other words, your device has both an IPv6 and an IPv4 IP address, so you assign both to the interface. And Microsoft Windows supports this. So by default, Microsoft Windows, you'll be able to set both an IPv4 and an IPv6 address. The nice thing about all this is, even though there's two versions of IP, there's really only one version of TCP and one version of UDP. So we don't have to have a lot of different iterations of different protocols that we have to support in different versions. There really is only one version of TCP and one version of UDP that sits on top of IP in the stack. And of course, at the physical layer, we pretty much all use 802 standards for the physical layer, so we don't have to worry about different standards there either for the most part, although there's some variations of the 802.x standards. So with dual stack architecture, there's two versions of the entire TCP/IP protocol suite, one for IPv6 and the other for IPv4. And like I said, this is supported by Microsoft Windows by default. So tunneling is basically a network protocol technique where we transmit a packet in a format that's otherwise incompatible with the network by encapsulating it within another packet. In other words, if we have an IPv4 network, we can carry IPv4 traffic inside an IPv6 tunnel. So basically, nodes, like let's say I have an IPv4 devices on my network, I can essentially send, and let's say I have other networks that are IPv6, I can essentially communicate with the IPv4 by having my IPv4 packets tunneled in my IPv6 network until they can get natively to the IPv4 network. So we simply take all that traffic, encapsulate it. Not terribly efficient way to do it, but it could be done. This is one of the methods that's used. I don't suppose this is used as often today as it used to be because we have some better protocols now. But this is one of the options: tunneling IPv4 or tunneling IPv6 over an IPv4 tunnel and vice versa. All right, so to manually create an IPv6 over IPv4 tunnel, it can be created in Windows Server 2012 when it's configured as a router using this command. So that's how you would create your tunnel for IPv6 over IPv4. Another option we have is intra-site automatic tunnel addressing, or ISATAP, used to send IPv6 packets between dual IP layer hosts across an IPv4 network. So this is enabled by default in Windows 2012, ISATAP. Addresses have the following format, so they start with FE80. So you'll need to add DNS-A record in your host file in order for ISATAP to work. So it would look like this. So you would add an A record. That's if you see on the bottom of that host file, that is a new A record. We'll talk more about DNS and what A records are later on. But you add a static. You could also do this in DNS, by the way. It doesn't necessarily have to be done in your host file, but you can see here we have the record for ISATAP added with a static IP address, an IPv4 address. So another option is 6-4 tunneling. So 6-4 tunneling provides automatic tunneling of IPv4 or IPv6 traffic over an IPv4 network. So it's a little bit like ISATAP. It can provide host to router or router to host tunneling, but it's most often used for router-to-router tunnels. In other words, I have various routers that we want to route IPv6 traffic between different routers using IPv4. So there's the 2002 /16 prefix, which we use for IP or 6 to 4 tunneling. The thing about IPv6, 6 to 4 tunneling is that you can only do this with public addresses, and that's why it's really limited to router tunnels and not host tunnels, host to host or host to router. So it's kind of limited its use. So the next best option is Teredo. Teredo is IPv6 over IPv4 tunneling that eliminates the requirement for to use public IP addresses or public IPv6 addresses. So it adds the ability to traverse NAT routers, which is one of the reasons that we couldn't use 6 to 4 over host networks. One of the limiting factors is it doesn't support NATing, but Teredo does support NATing. It has 3 components: the Teredo client, the Teredo server, and a Teredo relay. So a Teredo address can be identified by the Teredo prefix 2001/32 subnet. So again, we talked about a couple different technologies that we can use to transition to IPv6. You've probably noticed here I'm kind of grazing over IPv6 a little bit. There's certainly a lot of supplementary information about IPv6 that you could investigate, learn more about IPv6 and how it works. But for the most part, I think we don't really see wide utilization of IPv6 in our Windows networks. It certainly is happening a lot more today than it used to. But it seems like the adoption of IPv6 has somewhat stalled at this time. So it's not as common as I think a lot of folks thought it would be by now. But it certainly is something we need to be aware of. So in this unit, I talked about TCP/IP. That's a network protocol that's used to deliver data packets on a computer network. And remember, at TCP level, those are segments, not packets. We talked about IPv4 and IPv6 and how they're both supported in Windows 2012 and 2016. We talked about how an IPv4 address is formatted and a little bit about the different classes and interclass or classless interdomain routing. We talked about subnetting in IPv4 addresses. And we talked a little bit about supernetting, which isn't as common, but that's where you combine different subnets to make a supernet. We talked about some of the command line tools that we can use for debugging and for testing things for IP and IP connectivity. And then I talked about IPv6. We learned a little bit about their addressing, which again is much more complicated than IPv4. And we learned about the different types of IPv6 addresses and how we can transition from IPv4 to IPv6. In other words, how we can handle both IPv6 and IPv4 within the same network architecture. And that's it for this unit.